A couple different things. Current is the flow of charge. It just says how much charge passed a given point in a given amount of time. So I, which is our symbol for current, is equal to charge divided by time. Or as you'll see it on your equation sheet, Q over T. So a certain amount of charge passes a point a certain amount of time. That is our current. Usually this refers to charge flowing through a wire, but you can use it to refer to any type of charge that's flowing from one point to another. Like in the cell, when you have charges that are moving from one side of the cell to the other, you set up a current. So these are measured in amps. Charge, remember, is coulombs. Time, of course, is seconds. And 1 coulomb per second is equal to 1 amp, or 1 ampere. You might see it as amp, or you might also see it just as a capital A, and that's what I'll use. But you've probably seen this on some of your electrical devices. They will sometimes have a current rating, so whatever current they're built to use is listed usually on the electrical device, and it's listed in amps. So that's current. We also have resistors. A resistor is slows the flow of charge. Of electricity. That's why it's called a what? A resistor, right? To resist something means that you oppose it or you try to slow it down. So a resistor is just a device that slows down the flow of electricity. This is useful in circuits when you're building circuits to make the charges do whatever it is that you want them to do. You can think about a resistor as a pipe. So if I have a pipe with water flowing through it, that pipe has has a couple different dimensions. I have one dimension down here, which is the area, A, and then I also have the dimension, the length of the pipe, L. Right, so like we did with the capacitors, I'm going to ask you a couple questions. And you can tell me what happens to the resistance of this device. All right. If I make the length of this device longer, does that cause the resistance to go up, down, or does it remain the same? Right. You can think about it as a pipe. Really, we're talking about, say, a piece of wire. Right? I want to measure the resistance of that wire to electricity. But you can think of it as a pipe, water flowing through a pipe, and it's the exact same amount, the exact same physical response. So if I have a wire and I make it longer, what happens to the resistance of that wire? Will it resist electricity more? Will it resist electricity less? Or will it resist electricity in exactly the same way as before? If I take a wire and I make it longer. Or you can think about it in terms of a pipe. If I have a pipe and I make it longer, is it easier, or excuse me, is it more difficult to push water through that pipe? Is it easier, less resistance, or is the resistance the same? I'll stop at 105. 105. All right, A is the right answer. All right, think about your water hose, or if you have a water hose, or have you ever siphoned gas out of a car? No. We use to siphon gas out of cars a lot. And it's nice when you're siphoning gas to have a very short hose, because it's a lot easier to pull gas out of a car as a short hose. You know how to siphon it, like where you put and then you pour it into a bucket or whatever? Don't do that, huh? Then if you have a really long hose, it's very difficult to pull any amount of liquid through that. So if you increase the length, the resistance is going to increase. So A is the right answer. What happens, on the other hand, if I increase my area? If I increase my area, what happens to the resistance of this wire? If I make the wire bigger in area, does the resistance go up? More difficult for electricity to flow? Does the resistance go down, or does the resistance stay the same? Or you can think about it in terms of a pipe with water flowing through it. Is it more difficult to push water through a bigger pipe? Less difficult to push water through a bigger pipe? Or the same difficulty, the same resistance? Just a few more seconds. I'm going to stop at 50. All right, B is the right answer. Good. If I make that area bigger, a bigger pipe, it's easier to push water through a big pipe than it is through a little bitty pipe, right? So if I make the area bigger, that means that the resistance decreases. This is all in this expression for resistance, kind of like what we have for capacitance. The resistance is equal to L over A. If L is bigger, resistance is bigger. If A is bigger, resistance is smaller. There's also a constant here, don't worry too much about it, but it's that rho. So this is just, this is called the resistivity. It describes the material. Some devices have a greater resistivity than other devices. So for example, copper and wood. Which of those has the bigger resistivity? Copper or wood? What do you think? Wood. Right, wood is an insulator. It's not a very good conductor of electricity. That means it has a very high resistance, and so this measures that. So wood, for example, has a higher resistivity than a metal like copper. That is different for different materials. We'll talk about resistance again. Oh, one other thing. This is also sometimes called impedance. Impedance is more of a general term, but it'll come back up again when we talk about body scanning, because body scanners measure impedance. Y'all might have a body scanner back in athletic training, do you? Where am I? Who's athletic training? Oh, sure, athletic training, right? Who's athletic training? All right, this class is for athletic training majors. They're all out. Probably some accomplishment. Anyway, we'll talk about body scanners, and we'll probably see one when we go with the rec sensor, but they measure the impedance of your body. They run an electrical current through it and measure the impedance or the resistance of your body. But they talk about it in terms of impedance. All right. Okay. So one last thing for a couple things. This one. I'll hand back your exam in just a few minutes and give you a few minutes to write down the answers. This is sort of the basics of electronics, a law called Ohm's law, and it describes the relationship between current, potential, and resistance. It's written in different ways. I think in your book, actually, yeah, in your book it's written in this way. I is equal to V over R. They write it like this because if you think like this is my current, this is my potential. If I increase my potential, I increase my energy per charge, that's going to increase my current. If I increase my resistance, the resistance to current, increase this, that's going to cause this to decrease. So that's why they write it like this. But usually when you see Ohm's law, and the way you'll see it on your equation sheet is like this. V equals IR. This is just my voltage, our potential difference, our potential. This is my current. And then this is my resistance. So these three are related, and electricians use this a lot to determine for a certain voltage and a certain resistance what is my current, for example. All right, but you need to know how these things are related to one another. So as I said up here, if V goes up, my current increases because I'm increasing the amount of energy per charge, and that's going to cause my current to go up. If R goes up, then that causes my current to go down. Remember, R is our measure of the resistance to the flow of electricity. So if I'm resisting the flow of electricity more, that means my current's going to go down. I can draw a simple circuit. Remember, this is a battery. This is a resistor. You could see a simple circuit like this, something similar to this. Let's say that I have 10 volts here, and I have 2 ohms here. That's what I measure my resistance in. What is the current? Is the current let's see, 0.2 amps, B 20 amps, C 5 amps. What else could I do? Or is it D 10 amps? All right, what is my current in this circuit? 0.2 amps, 20 amps, 5 amps, or 10 amps? All right, so a few more seconds. I'll stop at 42. All right, C is the right answer. Simple here. I have my current is V over R. That's 10 volts over 2 ohms. That means that I have a current of 5 amps. That means that through this circuit, I have 5 amps of charge, 5 coulombs per second of charge that's flowing through this circuit. That's how electricians determine the amount of current that flows through a given device. They know its resistance and they know its potential, the voltage across it. They can find the current pretty easily. All right. Then I also wanted to find power. Anytime a resistor consumes power, if you remember, power is just a measure of energy per time. A good example of this is your bathroom heater or your hair dryer. Like if you're blow drying your hair, you have a resistor inside there. Next time you're using your hair dryer, look down into the barrel of it, and you'll see this coil of wire. That's all a hair dryer is. It's just a coil of wire, but it's a resistor. And that resistor will consume power, and it turns that energy into what for the hair dryer? Into what? No, not air. Heat, right. So it has a fan in there that will push the air, but it goes through that coil and it heats it up. And that's what you use to dry your hair. All right, so a resistor consumes this power. Look at your hair dryer when you go home, and you can see that little resistor inside there. Since I know that energy is charge times voltage, and I know that power is energy over time, that should be a lowercase t, then I can say that this is Q times V over time, but Q over T is equivalent to what that we've already seen? What is a measure of charge per unit time? Current, right, thank you. So this is I times V. So my power is just equal to my current times my voltage. You can go to your house, and again, electricians use this expression a lot when they're laying out household circuits, because you have to lay out your household circuit so that no individual circuit actually uses too much power. Because if it uses too much power, it could damage your circuit. It's going to be kicking your circuit breaker all the time off, right? Ever had your circuit breaker go off? Or a fuse or whatever? That's because you have too much current flowing through the circuit. And so an electrician, when they design a house, they have to figure out what is the power for each device, and then they calculate what is the current that is drawn by that device. So for example, your hair dryer draws a lot of current. It draws like 10 amps of current, which is probably the case. Usually your circuit breaker kicks off when you're using your hair dryer. Does that happen for y'all? When you're using your hair dryer, your circuit breaker kicks off? Or a bathroom heater maybe? Or, huh? In your camper, yeah. So generally those circuits are designed to handle that much current. Whereas something else like a radio uses just a very small amount of current. anyway, they use this expression to determine the amount of current for given devices. So for example, a light bulb, let's say it's a 60 watt bulb, that the power rating is 60 watts. And does anybody know the voltage in a house that a light bulb operates at? Right, 120 volts. Right, you don't need to know that number right off, but you've probably seen that number before because it's usually printed on your devices. If you live in a different country, it can be different. But in the US, we have this standard of 120 volts. And then if I want to know the current that is drawn by this light bulb, I just do P over V. That just comes from this expression. So that's 60 watts, over 120 volts. So that's equal to a half an amp. 60 over 120 is a half an amp. All right, I'm going to stop there.